Here are some quick notes on the end of Earth to accompany Chapter 6 of To Build a Star. So this is kind of a fun way to frame thinking about stellar evolution, I think, and also just an interesting question, what's going to happen to the Earth in the solar system? So stellar evolution on the main sequence, the definition of the main sequence is that core hydrogen is being burned and converted to helium, and that's going to create a more dense environment. And you can look at this really beautiful plot from quite a while ago made basically showing the structure of the sun today and at terminal age main sequence. So once the core hydrogen is essentially exhausted. A lot of information going on here. The vertical axis is basically a fraction or a relative quantity, so normalization. The horizontal axis it's a radial coordinate, but it's the mass fraction, so the total mass encompassed by the star. So really, you're looking most of this plot is like the inner, 25% or so of the stellar radius, but this is how things look in terms of mass. And so nowadays you can see that the core hydrogen is somewhat depleted. It's not all gone. At the end of the main sequence lifetime, in about 5.5 billion years, you can see here that the core hydrogen is basically burned away, is what will happen. And so then there's more helium. It's not so relevant for this quick notes, but you can see lots of other really neat things. Here, this X3, this is the helium-3 mass fraction. You can see that it's basically created by your hydrogen burning, but then there's not much created over here because there's not really any hydrogen burning going on. And the reason that there's a peak is that the further away you get from the core, the cooler it gets, so you can't really burn the helium-3. So like in the very inner region, you are creating it, but you're also burning it. In the very outer region, you're not really creating it, and there's this kind of sweet spot where it's maximized, where you're creating a lot, but you can't really burn it because of the temperature. All other kinds of neat things you can see here. But in any case, our hydrogen has been converted to helium in the core. It makes for a more dense environment. That's happening steadily, continuously as the main sequence continues. Now the reaction rate here is going to scale with the density squared, and so your energy generation rate is going to increase over the main sequence lifetime of the star, and therefore the luminosity is going to steadily increase as the core burning continues. And this turns out for the sun to be about roughly an increase of 1% of the luminosity every 100 million years or so, something like that. And so every billion years, you get a 10% increase in luminosity. Now what's interesting is though the sun has been steadily increasing in luminosity, the geological record shows that Earth's temperature has actually been decreasing if you take the very long view. So if you look at 500 million years ago to now, you naively would have expected maybe things to heat up because the sun's luminosity has increased, by about 5% in that time. However, there's complicated feedback in terms of greenhouse warming. So the greenhouse effect is actually reduced in the long view over time, and that's why the Earth has been able to maintain a relatively steady temperature. You use this as evidence to appease your crazy uncle that he's right, that there's no global warming. Keep in mind that this record here, this is the current temperature increase. What makes it frightening is just how crazy steep it is, right? And it is directly linked to our increase in greenhouse gases, and it's a problem. Okay, so what happens a billion years from now? So we know that our brightness is increasing roughly 1% every 100 million years. So then about 1.2 billion years from now, there will have been about a 12% brightness increase. That's kind of a critical point, because here what we're looking at is the increase in basically solar luminosity in percentage. And when you get to around 12.5%, you see what happens for the Earth's atmosphere, according to this atmospheric model, that the water vapor content basically jumps. You get sort of a big jump here, and that means the atmosphere has a high moisture content. And moisture, just this water vapor, has a large opacity to the infrared light. So what happens then is because there's a high opacity, that's going to limit any radiative cooling. Right? When those infrared photons from the surface of the Earth try to escape, they're just trapped by that cloud of gas. Now, also that means that you have this layer relatively low in the atmosphere is getting heated. So it's getting hotter. And what happens then is you also then have a temperature inversion. So you may remember from our isothermal atmosphere that we discussed a while back, covered in the quick notes on the Earth's atmosphere, or yeah, the simple atmosphere models, that the temperature is roughly isothermal, but really it decreases steadily as you increase in altitude above the surface of the Earth. In this case, when you heat this layer in the atmosphere, you create a temperature inversion. So it's actually even a bit hotter above the surface of the Earth than right at the surface of the Earth. And so this then shuts off convection. So now you're not only not radiative cooling, but you're also not really cooling by convection. And so what happens then is around that 12.5% increase in brightness, that's going to happen about 1.2 billion years from now, there's an abrupt jump in the temperature, the average temperature on the surface of the Earth. And so this abrupt jump takes you to something like an average global temperature of around 140 degrees Fahrenheit. So for reference, the current average global temperature is closer to like 60 degrees Fahrenheit. This 140 is something close to the world record temperature, highest temperature ever recorded. And so in about 1.2 billion years, the Earth will be, let's say, quite inhospitable to anything, like a person. Right? It doesn't mean nothing could live, but you're into the things that live underground, extremophiles, very hardy creatures that are not us. Once about 2 billion years from now, then the sun's brightness will have increased about 20%. At this point, the water vapor content is so high that you have just a bunch of water being lost to space. So a huge amount of your water content is up in the atmosphere, and that can escape some of it. And over about 1 billion years, we lose actually all the water to space. Sometimes it's written that the Earth's oceans will boil, and as far as I can tell, the current atmospheric modeling research for the Earth shows that actually you'll lose the water first before you're hot enough to just straight up boil it all away. But in any case, in about 2 billion years from now, that's the end of water-based life on Earth. So I'd say, ballpark in about 1 billion, probably maybe before that, but about 1 billion, it's over for humans, I would say, if we haven't blown ourselves up yet, which we certainly will have. But in 2 billion years, you won't really have water-based life anymore. So what about the Earth itself, though? When does it finally bite the dust? Well, around 5.5 billion years from now, then the sun will have depleted its core hydrogen. So you have this pressure, from the luminosity from nuclear burning at the center of the sun, that'll disappear. That causes the core to contract, right? Because there's not as much pressure. Gravity's going to start to overcome that. But then by the virial theorem, that contraction causes the core to heat up and the inner region of the star to heat up. Before it's hot enough to fuse helium burning in the core, you can actually start to burn hydrogen in a shell around this roughly inert helium core. Now, just like with core hydrogen burning, when you do shell hydrogen burning, it's going to act like a thermostat, right? So if the environment begins to cool down, it'll contract. That contraction will cause heating. That'll speed up the reaction rates. Energy generation will increase, and the environment temperature will increase, but then it'll expand, right? So it's just the usual thing for a star. It acts like a thermostat. It keeps itself at roughly a constant temperature. And so your total kinetic energy of this region of, the core plus the inner hydrogen shell, it stays about the same while your shell hydrogen burning is going on. And in this transition from core hydrogen to shell hydrogen burning. However, your core has contracted, so your potential energy has decreased. Well, if you want to maintain overall equilibrium, virial equilibrium, then you need the potential energy to increase somewhere else, right? If your kinetic is fixed, the potential in the inner region has gone down, then the outer region where the shell is at, it must increase, and therefore the shell must expand. And this is known as the mirror principle in stars with shell fusion, so shell burning. So basically what that means is if the core contracts, then the shell is going to expand, and if the core expands, then the shells are going to contract. So practically speaking, what does this mean? Is that basically the radius is going to expand, and over the course of a couple billion years, it's going to engulf most of the inner solar system. So what's shown here is the age of the sun. This is the radius in the vertical direction. And this dashed line, this shows you the Earth's orbital radius. So we're seeing the solar radius here, and then that's the Earth's orbital radius. You might wonder why there's this abrupt jump. That's because you have a whole bunch of mass loss going on in this red giant branch phase. And because there's mass loss, the Earth's actually going to pop out at a little bit further distance. So at this point, the sun has expanded a lot, and the luminosity has also increased quite a bit, and so the sun would be, or the Earth rather, the surface of the Earth would be crazy, crazy hot. But it gets worse, because what you need to do is you actually need to also take into account the fact that there's gravitational tidal interactions between the Earth and the sun, and there's also drag, right? When you're this close to the surface of the Earth, there's a strong, or surface of the sun rather, there's a strong solar wind, there's going to be basically friction, and so what happens is your orbital radius for the Earth is just going to plunge into the sun, and obviously it will cook up, and that is how the Earth will ultimately end. And with that happy note, that is it for these quick notes on the end of the Earth.